This is the second of 3 lectures from Chapter 7, and it's continuing talking about our current model of the atom, which is called the quantum mechanical model of the atom. So we've talked about a lot of different models of the atom. The quantum mechanical model that we're talking about now continues to be our currently accepted model of the atom. So that's important for you to realize. There were several scientists who contributed to this quantum mechanical model of the atom. One of them that we've mentioned before is de Broglie, and he's the one that said matter, particles of matter, can also behave as a wave, just like light can. And as a matter of fact, he put forth, and there's continuing evidence to suggest he was correct, that the larger the matter, the larger the mass of the matter is, the smaller its wavelength. So de Broglie suggested that matter as large as a human being or an automobile, for example, were associated with wavelengths, but the wavelengths associated with large matter, particles of matter, was so small that they could not be observed. On the other hand, the subatomic particle, an electron, is small enough that the wavelength associated with it is large enough to actually be able to investigate. So just to kind of be able to visualize his idea, if you imagine a nucleus, and let's put an N in there, and then remember that Bohr said that there were set energy levels that held the electrons outside of the nucleus. And what de Broglie then said was that the electrons that are in these energy levels surrounding the nucleus set up a wave pattern, and that each of the waves associated with each energy level has a particular wavelength and energy and frequency. To be able to visualize de Broglie's idea, I think this image kind of helps personally. So if you have a wave pattern that is of the wrong wavelength, the wrong frequency, think of it as not fitting inside a particular energy level or not fitting around the perimeter. Whereas if you get the right energy, frequency, and wavelength of a wave pattern, it will fit perfectly in a particular energy level. And so every energy level is associated with a particular energy, frequency, and wavelength of light. So it became clear at this point that to better understand the behavior of electrons, if indeed they were associated with wavelength, that scientists should turn to the knowledge we had about light, which was pretty well studied and very well, much more understood than the pattern of an electron as far as wavelength, energy, and frequency relationship. So the next few slides are going to be going over some of the basics we know about light and its behavior as a wave. Let's go over a couple definitions first. The distance from one peak to the next peak, or one trough to the next trough in a wave, is called wavelength. Okay? And that's a distance measurement. So it might be in meters, centimeters, millimeters, etc. Okay? Any distance measurement would be an acceptable unit for a wavelength. The symbol for wavelength, which you need to get familiar with, is this lambda. And the other property of a wave that you need to become familiar with, if you're not already, is frequency. Frequency, let's say that you had a couple points set up, and let's say your wavelength is traveling in that direction. So the frequency is how many wavelengths pass a particular point in a certain amount of time. So if you have, let's say, a high frequency, that means you've got a lot of waves passing in this certain amount of time. If you have a low frequency, you have fewer waves that pass in that same amount of time. So the units for frequency, and here's the symbol first of all, I call it a crooked V, that's frequency. The units are inverse seconds, and anytime you see this exponent of a negative, it means the inverse. So seconds raised to the negative 1 power is the same thing as 1 over seconds. So you will see frequency units expressed as either seconds raised to the -1 or 1 over seconds. So you can kind of think of it as cycles per second. That's the units for frequency. Another important property of light is that light travels at the same speed regardless of what its wavelength and frequency are. And that speed is 3 times 10 to the 8 meters per second. So all types of light, whether it's ultraviolet light, visible light, gamma rays, any type of light is going to travel at this same speed. That is a constant. All of the different types of light collectively, each with its own wavelength and frequency, put together are called the electromagnetic spectrum. So let's look at it for a minute, just so that you realize that all of these are types of light. Every wavelength and frequency in the electromagnetic spectrum is called light. We as humans often think that light only refers to visible light. But as you can see, visible light is a teeny tiny little fraction of all of the types of lights available. So at the highest energy range are gamma rays. At the lowest, at the lowest energy range, we have radio waves, microwaves, okay? So visible light has a moderate energy. We have learned about 3 properties or 3 variables that define the different types of light. And they can be put together in this equation, which is an equation you need to know. And C stands for the speed of light. So what this equation tells us is that the speed of light, which we know is a constant, 3 times 10 to the 8 meters per second, equals the wavelength of the particular light times the frequency of that same light. So wavelength times frequency will always equal 3 times 10 to the 8 meters per second. You need to be able to rearrange this equation for light to solve for frequency and to solve for wavelength. I want to point out that when you do rearrange this equation, notice that C, the speed of light, is on the top all the time. If you don't care to do algebra, if you're one of the people, many people who struggle with that, here's the triangle that goes with this equation. Okay, so all you have to remember with these triangles is you remember the variable that's on top, or the factor that's on top. It really doesn't matter the order of the 2 variables on the bottom. So again, to use this triangle, you're going to cover up what you're solving for. So let's say we're solving for wavelength. So you're going to cover up wavelength, and you're going to look at what's left. Wavelength equals C over frequency. Okay, wavelength equals C over frequency. Alrighty, so we'll be doing several calculations with that. I want to take a minute and I want you to think conceptually about the relationship between wavelength and frequency. I have drawn 2 different waves here with different frequencies and energies. And so I would like you to look at both of them and be able to tell me which of these 2 waves has higher wavelength, larger wavelength, and which of these 2 waves has higher frequency. So take a minute if you want, figure that out in your head, and let's see. So remember that wavelength is the distance between one crest and the next. So here's the wavelength for the top one. Here's the wavelength for the bottom one. So which one of these two waves has a larger wavelength? The top one clearly has a larger wavelength. So we'll call this one smaller wavelength. What about frequency? Well, frequency is the number of waves or wavelengths that pass in a certain amount of time. So here we've got 1, 2, about 3. If you look at the bottom one in that same, approximately that same distance, we've got 1, 2, 3, 4, and going on 5 almost. So the bottom one has a larger frequency, or higher. Higher is probably the more common word used. And the top one has the lower or smaller frequency. Okay, so look at this. What is the relationship between wavelength and frequency? What is the relationship between wavelength and frequency? There is an inverse relationship between wavelength and frequency. That means that as one of them goes up, the other one goes down. So if you look at the equation we just went over, where the speed of light is wavelength times frequency, you can also see the inverse relationship here. I always kind of thought it was ironic that if there's an inverse relationship, the two variables are multiplied by each other. Because if you just look at that, it just, to me, feels like it should be direct. But if you think about it mathematically, if the product of these two multiplied is always a constant, always the same, that means that as one of them goes up, the other one has to go down. Otherwise, the product of them won't remain a constant. So kind of like a teeter-totter. One goes up, the other has to go down. Alrighty. The other important feature or property of light that I want you to understand, have a grasp on, and be able to do calculations is all focused on this equation, which is one that Einstein worked with. E equals h nu. This frequency thing, its name is called nu, just like the wavelength is called lambda. Okay, so what this equation tells us is that the energy of light is equal to, whoopie-daisy, some constant. This h is called Planck's constant, and of course, as at any constant, it'll be given to you. Oh, bark fest time. All right, and of course, this is frequency. The nu, the crooked V, stands for frequency. If you're unsure about those symbols and what they stand for, you make sure you jot them down someplace on a note card or something so you can get real familiar with them. So what is this equation telling us? It's telling us that energy is directly related to frequency. Remember that h is a constant. So as energy goes up, in order for h to remain a constant, frequency must always go up. And that's because they're on opposite sides of the equal sign. So energy and frequency are directly related. Let's look at these two waves again. The top wave we described as having a larger wavelength, and so therefore the bottom one had the smaller wavelength. Remember, this is wavelength. Okay. And then we talked about frequency, and we said the top wave had a smaller frequency. There are fewer crests per unit time, and the bottom one had the larger frequency. And so we talked about wavelength and frequency being inversely related. One goes up, the other goes down. Now let's throw energy. What can you say about the relative energy of these two waves? Remember what I just told you on the last slide. energy and frequency are directly related, which means as one goes up, the other goes up. So that means since frequency is smaller on the top, that means the energy is also smaller on the top compared to the bottom. And the energy of the bottom wave is larger than the energy of the top wave, just like the frequency of the bottom. So if you basically think of it this way, the more waves you see, the higher the frequency and the higher the energy. So this is a higher energy wave. So if I showed you two waves or asked you to draw a model of, let's say, a gamma ray versus a radio wave, the gamma ray would look like this, very high energy, and the radio wave would look like this. Okay? Here are the two equations in a nutshell. So let's say that I gave you the wavelength, so given, let's see, is the wavelength, and I asked you to find energy. Look at these two equations and tell me how you would do that. If I gave you wavelength and I asked you to find energy, you might say, well, I use this one because it has wavelength in it. But this one would not give you energy. What would it give you? It would give you frequency. So if I gave you wavelength and asked you to find energy, it would be a two-step process. You would use this equation to first find frequency, then you would plug that value of frequency in to the second equation and solve for energy. An alternative to doing the two-step calculation is to combine these two equations into one single. So that would be this one. So if you want to commit, I would not give you this combined equation on a test. I would give you the two individual ones. So if you would prefer to memorize this combined one, if that seems easier to you, go for it. Again, H and C are constants that I would give you. I'll give them to you right now so you can work problems. H is Planck's constant, and it's, I hope I get this right, 6.626 times 10 to the minus 34. C, the speed of light, is 3.0 times 10 to the 8 meters per second. Alrighty. Here's a very typical type of problem. These are pretty easy to solve as long as you know how to rearrange the equations. So let's look at them again. Here are the equations that you will be working with. And here are the constants. I should have waited to write them on this page. Alrighty, so I would suggest putting the video on pause and seeing if you can do this relatively simple calculation. Let me give you the triangle for each of them in case you're algebra challenged. Alrighty, so go ahead and give it a try. Look here, and this is what you have to be careful of, is units in these calculations. So I will go ahead and give you the conversion factor to get from meters to nanometers, but then you need to be able to do that conversion. So here it is. 1 times 10 to the 9th nanometers equals 1 meter. That is your conversion factor. That's something I would give you on the test, the conversion factor too. So let's go ahead and work out that problem, see what we get. Since the problem is giving us frequency and it's asking us for wavelength, we only need to use one of those two equations, and that is the speed of light is frequency times wavelength. We are solving for wavelength, so we need to rearrange this equation to solve for wavelength. So wavelength equals speed of light over frequency. And now you can go ahead and plug your values in. Speed of light is 3 times 10 to the 8 meters per second. Frequency is 4.2 times 10 to the 18th Now, I forgot to tell you this earlier, but hertz is kind of a nickname or catch-all phrase for 1/seconds. Okay, so you can use hertz for a shortcut, or you can just write 1/seconds. So here are the units for frequency. Notice now that seconds cancels out, and meters is the unit you are left with. So what you get here are 7.1 times 10 to the minus 11 meters. But this problem asks for you to put it in nanometers. So now let's go ahead and convert. 7.1 times 10 to the minus 11. See, they're waiting for you to guess the wrong thing and not convert. Meters. There's 1 meter. 1 times 10 to the 9th nanometers in 1 meter. And so when you multiply that out, you get 7.1 times 10 to the minus 2 nanometers. All right, that's it. Here's another problem, and as always, I strongly suggest that you turn the video off and try to do it on your own. In the meantime, so shut me off if you want to check your answer. Here I go. This problem is giving us the energy of a wave, and it's asking us to find the wavelength. If you look at the two equations, okay, we are trying to find wavelength, but we can't find wavelength directly given energy because this equation doesn't have energy in it. So before we can find wavelength, we first have to plug in energy, which is our given information, and get frequency. Once we have frequency, we can plug that value into the second equation and solve for wavelength. All right, so let's use the energy equation first because that's the information we have. Energy is 4.41 times 10 to the minus 19 joules. Get familiar with that. You probably are familiar from chapter 6. That's a unit for energy. Planck's constant is 6.626 times 10 to the minus 34. And I've run out of room. Well, I can squeeze it in, times frequency. If I rearrange this to solve for frequency, I find that frequency is... It's a good idea when you're doing these calculations to remember some real fundamental rules of math. So remember when you're dividing exponents that you're really subtracting them. That'll give you a rough idea of what the value of this should be when you plug it into your calculator. So if you take the two exponents, minus 19, and subtract the bottom one from the top one, okay, two minuses make a plus, that means that you should get for your exponent roughly positive 15. So it's very common to plug these values in wrong and get the wrong order of magnitude for your exponent. So please, even if you're just listening to me and not try it on your own, please get your calculator out and make sure you're using it correctly. The answer, the correct answer, if you plug it into your calculator, is 6.66 times 10 to the 14. Frequency, remember what the units are? Either hertz or 1/seconds. That, my friends, is only step one. That is frequency that we found, and this problem is asking us for wavelength. So I'm going to open up a new page and do the second calculation. Now that we have frequency, I'm going to plug it in here and solve for wavelength. Alrighty, So now the equation I'm interested in is the one that relates wavelength and frequency. So I'm going to plug in what I know. I know the speed of light, and I'm going to solve for wavelength, and I just calculated frequency. Right, so rearrange to solve for wavelength. Divide both sides by 6.66. Okay, so let's do that quick little exponent check. 8 minus 14 is minus 6. So the exponent should be somewhere around minus 6. It can be plus or minus 1 of that. So the answer is the wavelength equals 4.50 times 10 to the minus 7. The units that you get from this equation are meters. Remember, wavelength is a distance. If you look back at the problem, they ask it for nanometers, so let's go ahead and do our conversion. Okay, 10 to the 7 meters. I gotta stop writing so big. Okay, 1 meter is equal to 1 times 10 to, whoops, that's minus 7, 10 to the 9th nanometers. So now you multiply 4.5 times 10 to the minus 7 times 1 times 10 to the 9th, and you get 450 nanometers. That's it for this lecture, and there's one lecture left for Chapter 7.